else is still in the
dispensing, potting and encapsulation challenges. Miniaturization and 3D assemblies continue to present manufacturing challenges to package assemblers. Likewise, material characteristics such as viscosity, needle drip, outgassing of air bubbles, etc. Present process challenges. So these production issues are going to be discussed today by our expert panel, and I'm delighted to be joined by, from right to left. On the end we have from Henkel, David Edwards. And next to David is Nico Coenen from MYCRONIC. And to my right we have Heakyoung Park from Nordson ASYMTEK. So I think you're referred to as Jeannie, and make it
Jeannie.
Yeah, okay. Thanks. So, thank you for joining us today. We're going to get started straight away, and my first question was really related to thermal interface materials, and are TIMs better than conductive adhesives for stacked die applications? Now that's a good one for Henkel to start on.
Certainly,
so let's start with you.
I mean, conductive adhesives can be considered a TIM material, but if you're referring to more of the traditional TIMs where you have your gap pads or your film type things, adhesives are pretty much better than that, just because in many cases you want to adhere the die to each other, and especially in stacked die applications, so you'd need that adhesion of the conductive adhesive.
You have the problem with the oozing out. Is it not better having a pad or a film material?
Yeah, I mean, you'd have to be able to control the amount of material that you're putting down. Or there's also, like die-attached film type adhesives that are thermally conductive. That then you can control the amount of flow and the gap, the bond line thickness of the material.
Ginny, what's your view on this?
Well, I can see the functionality on TIM and the conductive are somewhat, have a different kind of purpose, right? So, in TIM, in case it's like maybe the first level, like MPU, and then you put the TIM material and you have a metal cap. So you try to have the heat to go up, and then a lot of conductive, a lot of die-attached material. Main purpose is really the conductivity aspect, but the thermal also is very beneficial. But a lot of times, heat also goes kind of more downward. So I guess depending on what kind of packaging we're talking about, I think the TIM has a certain place, and conductive adhesive also has certain place.
Right. Okay. Nico, do you have any experience?
No, I fully agree there. I think it's really the application depending. I think both have their place, of course. So, absolutely.
Right. Okay. Okay, we're going to move on to our next question. What are the dispense process challenges that you come up with? Let's see. What are the biggest challenges you find with dispensing?
I can start.
Yep.
I mean, there's a ton of them, but I can start with, since we're talking about potting and encapsulations. A lot of encapsulation material, there's rheological behavior changes over time. And so there's a lot of times as a pot life you have to deal with. So a lot of manufacturing, when they have to deal with those changes and still have to ensure how, this very accurate volumetric accuracy and with a very stable process. That's really important. It's important. And also, because we're talking about fluid, there's a lot to lot differences in the manufacturing. There's operator to operator skill differences, and also, the hardware differences. So there's a lot of variations built in, and understanding what those are and be able to manage, and that would be really, really important for the manufacturing.
Right. Nico, you have obviously a dispensing system with your. Forget which iteration of the machine we're on now.
Yeah, it's the MY600. You mean?
MY600. What issues do you find most common? Do you run into most commonly?
I think there's, like Janie said, there's a lot of elements and factors. The challenge is to accommodate the application first, but also sometimes the throughput requirements to make it happening in production environments. First of all, if you do an application, you have to make it work. I mean, that is the first basic thing. So you have to make, from a quality point of view, make sure that it happens. But then sometimes you also have to see, okay, how does this work in a production environment? Because I mean, you can make something work which is really, really slow, and then you cannot transfer that process over to a production environment. The other thing, what Janie was saying, that okay, you want to have a process that more or less is where the operator is no worrying about anything. And so I mean, if you have viscosity changes over time, or the pot life is degrading, so that the machine itself take care of that.
Right.
So I think these kind of features are becoming more and more important for customers.
Right.
Dave, do you have any view on what
Yeah, I mean, they brought up the point of just the material consistency and the way that it drifts over time, viscosity, rheology, and compensating for that when you're doing the material. So either variation in the material itself or just variation over time because of the work life of the material.
So we're getting an announcement. So can we cut to commercial break?
Yes, 6:35, the IBC sales booth. Remember to get by there before the show closes.
Okay. So while it's doing that, Dave, is the sound loud enough? I'm a little bit concerned. Jeannie's hair seems to be hitting our microphone a lot. Is that coming through?
Okay.
Right, but is Jeannie's hair hitting? Actually, all right. Okay.
It's not. Okay, good.
Okay, let's see where we're at now. Right. And welcome back. Unfortunately, we had a short commercial break there while we were having booth announcements at the show. These things happen during a live situation. So picking up with my panel, Dave Edwards from Henkel, Nico Coenen from ASYMTEK, from MYCRONIC, and Heakyoung Park here from Nordson ASYMTEK. So my next question, guys, is really what are the most effective methods for controlling material deposition? Maybe you should start with that, JD, because you're closely involved in that area.
Yeah, I mean, that's a really good question, and there shouldn't be just one answer. Of course, we just talked about a lot of material rheology, so we have to really understand what kind of compound encapsulant we're trying to deposit, right? So understand the characteristics of it, filler, or what kinds of composition are associated with it, and then really look at what's the geometry of the parts that we're trying to handle, we're trying to dispense, and what are the volume that's required to do so. It could be really small volume of material, or it could be really larger volume of material, it could be a larger area with a very thin film. So really need to understand those requirements. So once you really understand those aspects, then you can really look into a lot of dispensing technologies that's out there. All has a great benefits, and if you really customers looking for a thin coating on larger area, we would look at some spray method or some kind of film coat method. If you're looking into larger reservoir dispensing, and there's a needle type positive shut-off dispense valves out there. There are also motor driven auger valves out there. So those are also have a good place. And also we have a lot of jetting technology that's out there. Even though, let's say, potting application, some customer maybe say, I need like a 2 milliliter of dispensing, and some customers say, still I need this small cavity, but I only need 16 nanoliter. So you have a very significant volume differences with the different tolerance. So we really have to understand those, what applicator really makes sense. And then there's also other attributes, right? Like a throughput aspect and quality aspect, what really makes sense on manufacturing floor. And depending on also the level of automation, what type of tool that will be really helpful to customer will be very key aspect. So we can see, understanding those, what applicator makes sense coming from really the application requirement.
Nico, what sort of different deposition systems do you have in with the MY600? I mean, you are doing jetting, but do you do other
Well, we have now more or less a full spectrum with our joint venture, of course, that we took in August. So now MYCRONIC does not only have the jetting valve, but we have now full spectrum of applicators as well. But I think to complement what Janie said, I think volumetric dispensing, if you're looking at from volume control, is probably the best way forward, controlling volumes all the time. Having said that, volumetric dispensing typically is related to needle dispensing, which then has a backdraw effect on typical outputs.
Right.
So what we see in general is that if a material is jettable, typically you would like to use a jet because most of the cases you will have a higher throughput out there.
Right, okay.
But it is really material depending, and also, well, what the application is, if you need a really small dot or a really big volume. So.
Right. What's your view on this, Dave? I mean,
you'd have to review the application and what is actually required and what is actually possible with that type of, with however the way the part is designed, what type of deposit you're putting down, and then once you characterize what the application actually requires and what the part requires, then you can look at the different techniques, whether it's jetting, whether it's pin transfer, whether it's screen printing, and then once you determine which kind of techniques would actually fit that particular assembly, then you can start working on looking at selecting a material that then would be compatible with that type of
what about
process.
Potting materials, for example? I mean, they sometimes come with voids inside them and that sort of thing. Is it better to deposit these things under vacuum? When you're doing
especially some of the two-part systems that are filled, you get separation just in storage, so you have to basically remix them and get the materials. So then you'd want to definitely put those under vacuum and pull any air out that you introduce into them. So, plus in potting applications, if there's any type of small areas or crevices that may entrap air, then definitely you need to have some type of degassing process under vacuum to pull those air bubbles out.
Okay.
I have some comment on
that.
If the vacuum was really required, then I can only imagine that will be a very expensive tool. So I think there's a certain market that really require that type of vacuum environment, because the outgassing and void would be very critical for high dollar value military application, radar, communication device. That may really make sense because of performance and cost, and also the critical reliability aspect by not having having void. That will be very difficult. But I cannot imagine, dispensing is a very common thing, but some consumer items, right?
The potting materials there is a protective barrier, basically.
Right.
So it's not going to be as effective if it's full of air bubbles.
Yeah, but I think in reality, if you really have to go to a vacuum process, it's going to be a very time-consuming process, and it's going to be a costly process. So I think, like Janie said, you have to really go into very specific applications that can afford that type of process.
Right.
And in the mainstream, typically I don't see that either have the time or can afford that cost structure to do under vacuum.
The integrity of the material itself, if there's a really no void, that'll really help.
A material that doesn't have air in it to begin with.
Yeah.
And then if you want to do a potting application or encapsulation process and not have any air bubbles, there's ways of doing that. It's the method and the technique that you use.
Right.
Either the dispense pattern, doing things like warming the part, and things like that. You can eliminate some of those entrapped air bubbles just from the dispense process.
Right.
So you can get around that, and it really depends on the application. Some applications may tolerate some amount of voiding. Some applications would have to have zero voids and zero bubbles. So.
Okay. So what are the common requirements then from customers that are looking for that are asking for potting applications? I mean, what do they?
As far as requirements,
what do they look for? Uniformity of the material? Do they?
Yeah, I mean, they just needs to have a material that's consistent, that they don't have to really do any modification of or alteration of it. A consistent material,
Okay.
But if I can comment on a little bit, because in manufacturing, not just the material itself, but the also easy of use depending on what tools that you're using, also how you actually manage the variations that we just talked about, and also if the customer is investing in certain tool to be able to automate the dispensing, the setup time, any downtime, that would be very critical because they wanted to fully utilize the tool, right? That's really going to give you high output. So there are other aspects besides dispensing that really required by the manufacturer, because they want almost no variation and stable process, right? That's the end goal, right?
Ease of use and stable process, and coming back to my thing about air gaps. I mean, air can cause trouble inside the device if it's trapped in there.
I think in general, what customers sometimes might do wrong is that in 9 out of 10 cases, they will look for a material properties that they think can do the job. Yeah. And then when they have selected the material, then they also think about, we also have to apply it. So, and I think sometimes it would be better for customers that they also think about how they're going to apply it together with the material choice, because then you can maybe eliminate a number of elements. And that is, I think, a common mistake that a lot of customers make, that they make a selection of a material based on their chemical properties or whatever, and then on a secondary they think, now we have to do it in production, and then they might face issues, we cannot jet it, or we cannot do it like that.
Yeah, that's a good point. Right. So the performance, reliability, but the manufacturability, that will be a really key aspect.
And this is key just up front to whatever information, as much information that can provide the material supplier with, as far as what their requirements are, what their dispense requirements are, what their parts require, and that's why we can select the right material to begin with, and help them, to get the right material on the first couple tries.
Okay. But many times there are two divisions. One is doing the selection of the material, and then it becomes to a design of manufacturing group. So these are two different groups.
Two different groups with different ideas.
With different ideas, and then is where the difficulty becomes.
Right. So it's very common for us to deal with selection of the material, which already meet the performance requirement, and then now we're evaluating what is most applicable in the manufacturing process. And then they narrow down to one final product, and those are very common process in the process development.
Right. Okay. What's the best method for controlling needle drip, for example, when you're doing dispensing?
That happens a lot, but the reason why that's happening is that we talked about void a lot. The fluid in the fluid pass, whatever the delivery system might be, if there's any void that's trapped in there, then you really run into irregular dispensing, and it's really difficult to control the volume. So it's very common practice in manufacturing that doing the pretty proper priming, depending on what applicator do you wetting from the fluid. So really try to minimize or eliminate the void trapment. Then you will know the dripping wouldn't really happen. And then also,
would you apply some heat to the reservoir to try and make the
not necessarily. It'll be first of all, the fluid itself shouldn't have any void. But some cases the air can be trapped when you deliver those fluid to the applicator all the way to the needle. So there's a proper priming that's recommended by the dispensing system. There's a guidance around it. And another case would be also some cases very simplistic time pressure valve. There's no shut-off mechanism. So some time pressure valve comes with a very positive shut-off. Then that'll eliminate the void issue. And there's also check valve that's out there that could also eliminate dripping. But once you see dripping, typically you really have to go down to whether I really wet the fluid properly. Then once that's kind of wrong, then you kind of make it difficult to really process and make a stable process.
Right.
So it's really setup related issues that can, the maybe operator and machine user has to be trained on.
Okay. Nico, do you have any view on this?
I think it's a matter of the fluid itself, and then based on that fluid, you're going to choose the type of valve that can also cover that. I mean, if you have a positive shut-off or not. So I think some of the applications, that the material is not or typically has not the tendency to drip. Other materials might have a higher risk to do that, and based on that, of course, you're going to see, okay, what kind of valve technology are we going to use to eliminate, to have a positive shut-off or whatever, and to eliminate dripping in as general.
Okay. So David, it's all your fault.
Yeah, I mean, that's something you just have to check, is to make sure the compatibility of the fluid with the dispense equipment. You know, in some cases, some fluids may be reactive with some of the you know, metal components of the dispense head. We've seen that issue.
Really?
So you can get, you know, you can start getting some gelation and stuff. So it's just really making sure that the fluid that you're using, the material that you're using, is compatible with the dispense systems that you're using, and they're capable of being dispensed in the way that they wish to.
So, how important is, or in fact, the next question was really going back down to our conductive epoxies. When would you use conductive epoxies? What's the best? When would you use conductive epoxies? Let's start with you on that, David.
Conductive epoxies. Any type of application that you require, you know, the conductivity, either electrical or thermal conductivity, and the adhesive properties of conductive adhesive.
Okay.
So when in those applications that you don't have any type of fixture, you don't have anything to hold the part in place, then you definitely want to go with a conductive adhesive.
You're working with maybe sensitive devices that can't take a lot of heat, basically. But a good time to use these, wouldn't it?
Yeah, I mean, if you know, for parts that take a lot of heat, you know, you do have some limitations of using the conductive adhesive. You can only go so high as far as the conductivity.
Okay.
So in those type of applications, then you probably definitely have to go with more of a film type of material.
Okay. How important is adhesion?
Well, adhesion is, I mean, in most applications, adhesion is very important because you want to eliminate any path for more moisture, any contamination to get into your part, to get to the active part of your part. So adhesion is very, very important. You know, but if you have some type of fixture or something to hold the part in place and to keep it under compression, you know, adhesion, you know, is not as big an issue. But even in that case, you want to have good wetting, so you can basically exclude any moisture, or any other type of contaminant getting into that part.
So I think I want to comment on adhesion-wise. It's people look at material itself, but there's also the board, the part integrity as well. You know, the cleanness of the surface is going to be very impacting on adhesion as well. And we run into sometimes issue when we're doing conformal coating. The boards were not really properly clean, so the wetting characteristics all just inconsistent. Then we have to really educate customer how to really properly handle those boards.
That's right.
So there's a surface, you know, there's a surface requirement in order to make a uniform wetting characteristics. And we run into those type of challenges with customers.
Right. So again, with miniature parts, it's better to clean before you dispense some of these areas.
I think in general, yes.
Yeah.
The question is, let's say if you have a conformal coating application, is it really necessary to clean? Because a lot of customers don't clean before they put the conformal coating.
That's right. I mean, I think the numbers are something like 60%, 60-40, something like that.
So if a very simple answer would be cleaning helps, yes. I'm 100% sure that it will help. Is it 100% necessary? Probably not in all cases, because a lot of the customers don't do it.
Depends on the size of
reliability requirements of the application.
The reliability requirements, the size of the board, and
how long the board has to last. I mean, if
you're talking about a garage door opener, if it fails, it's no big deal.
Right.
If you're talking about a pacemaker, if it fails, it's an issue. So for those, it really depends. Those high reliability applications, clean.
But I've never understood why so many people don't clean before they conformally coat. I would have thought it would make more.
It
is a cost, but I mean, I would have thought it would be nearer 80-20 than 60-40.
But I think it's a very cost-sensitive market there as well. So I think any process that you add to the cost process is seen as we rather not do it if it's not necessary.
Rather not do it if you can
because
avoid
if you
it.
do it and your competitors don't do it, you're maybe living in a better quality, but you're price position yourself in a worse way.
Yeah, yeah, absolutely. In what applications would you consider using a two-part epoxy? What sort of applications do you use these in, David?
Well, if you're using an application, especially like in a potting material that's room temperature curable, you really have to go with a two-part system because they're so reactive that one component you either have to store it at a very, very low temperature, minus 40, minus 60 C, and then their work life is very low.
Right.
So you'd have to use a two-part system.
Okay.
There's other applications in which you want, a lot of two-part systems you can mix and match the resin and the hardener system. So if you want to change, if you have a requirement where, you don't have very high temperature requirements, then you can use a room temperature curable hardener. But if those are applications that require higher temperatures or higher chemical resistance, then you can do, use a different type of hardener that has higher temperature resistance, higher chemical resistance. So you can, mix and match the materials to grow the properties that you want.
Okay.
Yeah, the automotive industry really common to use a two-part component, and one of the very critical aspects for them is once the time between mixing to actually deposit, the time is very critical.
Yes.
They have to really make that constant. So there is a really good case for the two component market. But also we had a good success with the pacemaker. One of the medical customer, they were doing a lot of manual dispense. It was a two-part epoxy has to be dispensed between electronic side to the header. So there's exposed wire, and you had to actually hermetically seal that area, and also had to be mechanically strongly bonded. It was a painful process in the past, and we were able to really address more automated fashion. In that case, two-part really was already approved by FDA, and it has to go into the body, so the material really makes sense. It was just really the manufacturability was painful.
Yeah, I would imagine you need to keep the mix as close to the point of dispensing as possible, because it obviously starts to cure the minute you put it together.
Yeah, I think from a dispensing point of view, I think everybody has looked at two parts as not the easiest way, because there's a lot of things happening as soon as the two materials start to connect. I mean, there starts the curing process, or you have either a statical mixer or a dynamical mixer, but then there comes a lot of maintenance and a lot of things around the process. I think my personal view on this is that I think you will see more and more two-part materials popping up because of the advantages that once you put them down, they're done.
Yeah.
So I do see a trend that two-part materials will become more and more common. And I also see that more and more dispensing companies are refining their two-part systems to become more user-friendly.
Okay.
Two-parts are typically more stable as far as, so you don't need to have a freezer. You don't have to ship them overnight.
Right.
So there's logistics and the handling of a two-part
The handling
system.
and the storage of them is simpler. Yeah.
And a lot of times, the one components are frozen, so you have to take them out and you have to let them sit at room temperature for 1 to 8 hours. A two-part system is, there's no downtime. So if your operator forgot to take the material out, the night before, and you show up to work, and now you have to wait 8 hours for the material to thaw out, and now you can't do your production. So that's an advantage of two parts.
I think the only real downtime is, as Nico mentioned, there's quite a lot of maintenance to it, in as much that you got to flush it out and make sure it's constantly kept clean, because that
two-part systems, you could just let them sit overnight and not have to clean them out all the time.
Okay, my next question is, what are the do's and don'ts of curing?
Do's and don'ts of curing.
Well, I will let them make sure to stick with the curing profile and specification. But there's a really good attribute about curing, because you can't just look at the technical data sheet on curing aspect, because one example would be UV curable, but you have a really different topography of the board, and you try to really cure the part, but there's a lot of tool component, then there's a shadowing effect. So there are certain component won't be really cured.
Right.
So in that case, the manufacturing really has to think about the secondary mechanism of cure, whether it's moisture or the heat.
Yeah, but in LED manufacturing, for example, it's critical the amount of time that the UV cure is exposed to the board, because it can affect the luminance of the lamp.
Yeah, I think the curing profile in general can have a quite effect, because if you ramp up your curing too fast, I mean, it can have a huge impact on how the material is reacting. So I think it is part of the process, and you cannot see it as a separate thing. So it comes together with the material and the whole process, actually.
Right, there's like solvent. If it's solvent-based material, solvent can be trapped, so the cross-linking is prohibited, and then curing is not going to be possible. And also bubble can be trapped if you try to do accelerated cure. So, you really need to be careful on the curing profile, and based upon also topography of the parts.
Right.
And you need to understand that, that whatever cure mechanism you're using, a UV cure, oven cure, whatever, you need to make sure that you profile that oven consistently. Just because the oven says 150 degrees Celsius, you need to check it. You need to make sure that temperature is consistent throughout the oven. You may have an oven and may have hot spots and cold spots, so you'll get different cure rates as far as when you put the parts in. And you need to also, when you're curing materials, you need to, things like ramp rate, cure speed and stuff are things that you need to take into account. Because some applications, some materials, if you cure them too fast, they either will exotherm, create too much heat, or they'll create too much stress on your part. So, it's really a lot of things like ramp rate and the actual temperature you cure it at can have a lot of impact on the end product and your material and your assembly.
Well, I think that brings us almost to the end of our program today. I want to thank our distinguished panel. From the right, Dave Edwards from Henkel, Nico Coenen from MYCRONIC, and Heakyoung Park from Nordson ASYMTEK. Thank you guys for joining us. And thank you for joining us, and with all our programs actually throughout APEX. This is bringing us to the end of our APEX programming. I hope you've enjoyed it, and we'd like to see you joining us again when we do the next one, which is probably going to be at the SMT Nuremberg show in May. And we will be encouraging, obviously, questions and some feedback from you to help us make these things more dynamic. But for now, this is Trevor Galbraith saying thank you for watching, and we'll see you next time.